Hello and welcome to our discussion of Chapter 3 in the Fundamentals of Database Systems. Uh, this chapter centers on data modeling using the entity relationship ER model. So ER diagrams are a very common thing that you'll see whenever you're talking about databases. So it's a good idea to be able to understand how you use them and where they come from and what you do with them. So the overview of database design processes. There are two main activities whenever you're dealing with databases. One is database design, so the actual tables and such that are going to be used to store. Additionally, there's application design. These two things have to tie together well. Sometimes there's another layer in between there, which is an interface design sort of element, but at very least you've got these two. The focus of this chapter is on conceptual database designs, that is to design the conceptual schema for a database application. Application design focuses on the programs and interfaces that access the database. Application design is a different sort of experience, generally considered part of software engineering. So you have to be able to design an application to meet users' needs and to follow best practices and patterns. Continuing the discussion, figure 3.1 contains a simple diagram that illustrates the main phases of database design. So it starts off with the kind of concept that you gather some requirements and some analysis. You start figuring out what the functional analysis are and coming up with some kind of documenting what those functional requirements might be. You come up with what is the high-level transaction specification. At the same time, in concurrency, you're basically doing some data requirements, coming up with a conceptual design. Then you come up with a conceptual schema, excuse me, a logical design where you do some data model mapping. And then also, once you've kind of done that stuff, then you move into the specifics of a particular solution, which is when you start talking about application program design. That's where you move from a conceptual to logical schema that's modeled in a specific type of database. Not all database systems have the same constraints or same capabilities, so you oftentimes have to customize it for your particular environment. There's also some performance considerations that generally are taken into consideration to ensure that the approach you're using is appropriate for the technology that's being utilized. There are methodologies for conceptual design. The entity relationship diagrams, that's what we're talking about now, is one of the most common ones. There are also enhanced entity relationship diagrams, chapter 4. We're skipping over that chapter in this course. But you also typically end up using design tools to do this to make it simpler. Just as we utilize tools when we're designing things in a physical world, such as computer-aided design, we utilize tools in technology and database design that allow us to be able to modify the design of a database on the fly in a controlled way and potentially even have it produce things for us like the actual scripts that are necessary to make it implemented for a particular database technology. The use of design tools in industry for designing and documenting large-scale designs. UML, very common, unified modeling language, is a very common way of documenting class diagrams. Fairly popular, maybe not as popular as it once was, but still kind of a standard way of designing software. So in this case, we're going to talk a little bit about an example company database. So we need to create a database schema design based on the following very simplified set of requirements for a company. The company is organized into departments. So the things that are all uppercase are essentially entities that you want to be paying attention to. Each department has a name, so that's an attribute, number, and an employee who manages the department. So somebody is tasked with managing. Of note, probably employee should also be all uppercase if you're doing this in a more proper way, because an employee is likely an entity. Each department controls a number of projects, so project is yet another thing, and each project has a unique name, unique number, and is located in a single location. The database will store each employee's social security number, address, salary, sex, and birth date. Each employee works for one department, but may work on several projects. So they have a primary department that is their department, but they then may be doing work on multiple projects. The database will keep track of the number of hours each week that an employee works on each project. So you need to be able to track the hours each project. It's required to keep track of the direct supervisor of each employee. So who's their boss, who's reviewing potentially their time, and so on. And each employee may have a number of dependents, and for each dependent, the database keeps track of the name, sex, date of birth, and relationship to the employee. Entities and attributes. An entity is basically, and I've already kind of started alluding to them, it's a basic concept in the ER model. Entities are specific things or people in this world that we're modeling. They're represented in the database. For example, an employee, John Smith, the research department, the product X of project or project X. Attributes are properties that are used to describe an entity. So they're characteristics of that entity they're associated with a given set of entities. For example, employee entity may have the attributes name, social security number, address, sex, and date of birth. A specific entity will have a value for each of its attributes. So you have values that are associated with an instance of an entity. For example, a specific employee entity may have name John Smith with a social security number of 123456789 and an address and so on. Each attribute has a value set or data type associated with it. So they are expected to be of a particular type, and everything that is a given attribute is the same type. So there's no variation amongst the different records. So if it's an integer for one, it's an integer for all, and so on. So continuing kind of a conversation around attributes, there are simple ones. Each entity has a single atomic value for the attribute, for example, sex or social security number. A composite attribute is an attribute that may be composed of several components. For example, an address, and an address is made up of apartment number, house number, street, city, state, zip code, county, and maybe zip code plus 4. The name is potentially a first name, last name, and middle name. Composition may form a hierarchy where each component are themselves composites. Multi-valued, an entity may have multiple values for that attribute. For example, the color of a car or previous degree of a student. Previous degrees, you might have more than one. So it's a set of attributes. In general, composite and multi-valued attributes may be nested arbitrarily to any number of levels, although this is rare. For example, previous degree of a student is a composite multi-valued attribute denoted by previous degree, college year, degree, field, and so on. And you have to do that essentially with a one-to-many relationship. Types of attributes. Multiple previous degrees values can exist for each four subcomponent attributes. So we model that a certain way. Here's an example of that sort of kind of decomposition or composite attributes. And it shows that there may be a hierarchy amongst these things. Entity types and key attributes. Entities with the same basic attributes are grouped or typed into an entity type. For example, the entity type employee and project. An attribute of an entity type for which each entity must have a unique value is called a key attribute of the entity type. For example, SSN of an employee. And it's actually a little bit more than that. It is something that is guaranteed to give you one and only one matching record if you were to query it, if it's going to be a unique key. A key value or key attribute may be a composite, so you may have a composite set of values that make the key. Vehicle tag number is a key of the car entity type with components number and state. So within the state of, say, West Virginia or Ohio, there will be a single value that identifies a given car, but there could be possibly two cars in different states with the same license plate, but they belong to different states, hence the composite nature of the key. An entity type may have more than one key. A car entity may have two keys. For example, it might have VIN, a vehicular identification number, popularly called a VIN, and it may have a vehicle tag number, which is the license tag plate that's put on the front of the car. Each one of those would be unique. You're primarily going to pick one of them as the key. A key is underlined. Note this is different from the relational schema where only the primary key is underlined. So primary key versus key, two different things, but generally speaking, a primary key will be a key, but generally speaking, you identify one of them, and there's, for performance reasons, that you're going to pick it. Entity set is each attribute or each entity type will have a collection of entities stored in the database called an entity set, sometimes called an entity collection. From the previous slide shows 3 car entity instances in the entity set of car. The same name car used to refer both entity type and the entity set. However, entity type and entity set may be given different names. Entity set is the current state of the entities of that type that are stored in the database. Value sets are domains of attributes. Each simple attribute is associated with a value set. For example, last name has a value which is a character string up to 15 characters. For example, date has a value composing of year, month, day, stored in some fashion where each letter is an integer. It's actually a little bit more robust than that because it may actually be a proper date. A value set specifies the set of values associated with an attribute. Value sets are similar to data types in most programming languages. For example, integers, characters, ints, reals, whatever they might be, bit. Mathematically, an attribute A for an entity type E, whose value set is V, is defined as A given E implies P of V, where P is the power set of V, which means basically all possible subsets of V. The above definition covers simple and multi-valued attributes. We refer to the attribute A of entity E as A sub E. Displaying an entity type in an ER diagram, an entity type is displayed in a rectangular box. So you draw a little rectangular box and typically give it a name. Attributes are displayed in ovals. So they're ovals instead of boxes. Each attribute is connected to its entity type. Components of a composite attribute are connected to the oval representing the composite attributes. Each key attribute is underlined. Multi-valued attributes displayed in double ovals. See the full ER notation in advance on the next slide. So basically seeing kind of the things that we just talked about, entity being a rectangle, weak entity being a double-lined rectangle, and so on. Entity type car with 2 keys and a composite or corresponding entity set. So figure 3.7, the car entity type has 2 key attributes, registration and vehicle ID. Notice they're both underlined and both inside of ovals. A is the ER diagram notation. B is the entity set with the 3 entities. So basically the corresponding mathematical set, if you will, of the instances. The initial conceptual design of entity types for the company database schema. Based on the requirements, we can identify 4 initial entity types of the company database: department, project, employee, and dependent. Their initial conceptual design is shown on the following slide. The initial attributes shown are derived from the requirements description. So here's the basic preliminary design. You'll see that there's a department that has name and number being potentially keys. Project has a name and number as well. Employee has a social security number, likely has an employee number too, but that's not modeled here. And then dependent has a date of birth, relationship, sex, employee that they're associated with, and their actual name. There's probably something that could be used to create a key there, but there's not a naturally occurring key. It would have to be some form of a composite. Refining the initial design by introducing relationships. So the initial design is typically not complete. There's going to be a relationship between the various entities. So in the ER model, there are basically kind of 3 main concepts: entities, attributes, we talked about those 2, and relationships. And the relationships in some ways may be the more important one. We introduce relationships next. So relationship and relationship types. A relationship relates 2 or more distinct entities with a specific meaning. For example, employee John Smith works on the product X project, or employee Franklin Wong manages the research department. Relationships of the same type are grouped or typed into a relationship type. For example, works on relationship type in which employees and projects participate, or the manages a relationship type in which employees and departments participate. The degree of a relationship is the number of participating entity types. Both managers and works on are binary, meaning they're between two things, relationships. You'll find that's probably going to be the more common case. Relationship instances of the works for N to one, so that's many to one relationship between employee and department. So a given employee may work for many departments, right? And a department may have many employees working for it, so to speak. Figure 13.13 is a many-to-many sort of relationship, so an M-to-N relationship for works on. An employee works on many projects. Projects have many employees working on that are being worked on by employees, so it's basically a many-to-many relationship. Relationship type versus relationship set. A relationship type is the schema description of a relationship. It identifies the relationship name and the participating entity types. Also identifies certain relationship constraints. A relationship set is the current set of relationship instances represented in the database, very similar to what we talked about earlier with sets. The current state of the relationship type. Previous figures displayed the relationship sets. Each instance in the set relates individual participating entities, one from each participating entity type. In ER diagrams, we represent the relationship type as follows. A diamond-shaped box is used to display a relationship type connected to the participating entity types via straight lines. Note that the relationship type is not shown with an arrow. The name should be typically be read from left to right, top to bottom. Continuing relationship, refining the company database schemas, introducing relationships. By examining the requirements, 6 relationship types are identified. All are binary. Again, going to be kind of common. Listed below with their participating entity types. Works for, so employees work for departments. Employees manage departments. Departments are controls projects, and employees works on project. And supervision, employees are supervises essentially another employee. That's something where it's potentially 2 different records in this same table that you're talking about. Unlikely that you're going to be supervising yourself, although could be, who knows. Dependence of is between an employee and their dependent. The ER diagram showing those relationship types are as follows. The figure 13.2 shows the ER diagram of the company database kind of coming together more. We've added the works for relationship between employee and departments. We've added the manages between an employee and a department, and there's one employee manages one department. The N and 1 on the various diagrams kind of show the cardinality associated with how many of something the relationship will enable or allow. In the refined design, some attributes from the initial entity types are refined into relationships. A manager of departments manages and works on, employee works for, and department employee works for, etc. In general, more than one relationship can exist between the same participating entity types. Manages and works for are distinct relationship types between employee and department. Different meanings and different relationship instances. There are constraints on relationships of various types. This is where I've talked a little bit so far about cardinality. This is also sometimes called ratio constraints. So cardinality specifies as maximum participation on each side of the relationship. A one-to-one is kind of the simplest. One-to-many or many-to-one is where there is many of one thing relating to another or vice versa. And many-to-many is there's many things to many other things. The existence dependency constraint specifies that the minimum participation, also called the participation constraint, is either 0, so it's optional, so they need not have an existence dependence, or 1 or more, mandatory participation, so you have to have the value or you can't exist. Existence dependent, so that basically means that one thing cannot exist unless the other thing does as well. Many to one relationships are as follows. Figures 3.9 shows pretty much some instances in the work for relationship set, which represents a relationship for works for between employee and department. So many employees work for one department. Many to many, this is an employee works on many projects, and a project has many employees working on their project. A relationship between the same participating entity type in distinct rows is a recursive relationship type. This is also called a self-referencing relationship type. This is the situation where the employee manages another employee. So employee participates in twice in two distinct roles, supervisor or boss, and so on. This is a relatively simple sort of variation of the theme. You can actually have it to where there's more than one entity involved. Each relationship instance relates two distinct employees entities. One of them is going to be a supervisor and one of them is going to be the supervisee. Displaying a recursive relationship, in a recursive relationship type, both participations are the same entity type in different roles. For example, a supervisor relationship exists between employee in the role of being the supervisor and between a different employee or another employee that is in the role of subordinate or worker. In the following figure, the first participation labeled with 1 and the second role is labeled with 2. In ER diagrams, you need to display role names to distinguish between the participations. Figure 13.11 is an example of a recursive relationship in a visual sort of approach. Recursive relationship type is supervision, participation, role names are shown, and this is basically showing the employee supervising themselves and so on, or supervising another employee, supervising an employee as a supervisee. Weak entity types, an entity that does not have a key attribute and that is identification dependent on another entity type. A weak entity must participate in an identifying relationship type with an owner or identifying entity type. Entity types are identified by the combination of a partial key of the weak entity type, the participation, the particular entity they are related to in the identifying relationship. Here's an example. A dependent entity is identified by the dependent's first name and the specified employee with whom the dependent is related. Might be first and middle name would be a better choice because you might have a situation with one dependent or two dependents having the same name. It's possible. Name of dependent is the partial key. Dependent is a weak entity type. Employ in its identifying entity type via the identifying relationship type dependent of. Attributes of relationship types. A relationship type can have attributes. For example, hours per week on works on. This is essentially an attribute of being associated to a relationship. Its value for each relationship instance describes the number of hours per week that an employee works on a project. A value of hours per week depends upon a particular employee project combination. Most relationships attributes are used with a many-to-many relationship. In a one-to-n relationship, they can be transferred to the entity type on the inside of the relationship. This is an example of the ER diagram with the company. The diagram, the notation is introduced gradually throughout this chapter, and we're going to summarize it in 3.14 later on. Notations, constraints on relationships. The cardinality ratio of a binary relationship is 1 to 1, 1 to n, to 1, or m to n, shown by placing the appropriate number on the relationship's edge. Participation constraints on each participating entity type, total called existence dependency or partial. The total is shown by double line, partial by a single line. Note these are easy to specify for binary relationship types. There's also alternative min-max notation for relationship structural constraints specified on each participation of an entity type E in a relationship of type R. Specifies that each entity E in the set of E participates in at least min and at most max relationship instances in R. Default, no constraint, is min 0 max n with no upper limit. Must have n less than or equal to max, and min must be greater than or equal to 0, and max must be greater than or equal to 1. Derived from the knowledge of many world constraints, so it's based upon what it is you're trying to model. Alternative MN notation for relationship structure constraints continued. A department has exactly one manager and an employee can manage at most one department. Specifies 0 to 1 for participation of employee and manages and 1 to 1 in the participation of department and manages. An employee can work for exactly one department, but a department can have any number of employees. Specifies 1 to 1 for participation in employee and works for, and specifies 0 to n for participation in department and works for. There could be a problem with this design, just playing devil's advocate, and in particular, this whole constraint here that a department is managed by a person can manage only one department. There may be situations where that could be problematic in a real world scenario. Oftentimes, you have somebody that takes over incremental temporary sort of management of a department as a general rule, so that could be a problem. Not a great design. The min-max notation for relationship constraints, employee 0 to 1, manages 1 to 1 department, and so on. Read the min-max numbers next to the entity, looking away from the entity type. Company ER schema diagram using min-max notation. We're adding the min-max to the notation. Alternative diagrammic notation. ER diagrams are one particular or popular example of displaying database schemas. Many other notations exist in literature and various database designs and modeling tools. Appendix A later on illustrates some of the alternative notations that are used. UML class diagrams is representing of another way of displaying ER concepts that is used in several commercial design tools. Although generally speaking, you don't see a whole lot of ER diagrams going on in database design. Here's a summary of the notation of ER diagrams. Revisiting, I believe we've seen this before. So UML class diagrams represent classes similar to entity types as large rounded boxes with 3 sections. Top section includes the entity type name, class. Second section includes attributes. Third section includes class operations. Operations are not in basic ER models. Relationships called associations represent as lines connecting the classes. Other UML technology or terminology also differs from ER terminology. Used in database design and object-oriented software design, UML has many other types of diagrams for software design. It's a thing unto itself. We could talk about ER or UML diagrams for the remainder of the term. Here's an example of a UML class diagram. You will occasionally see these, and I've actually seen some like this over the years. It's generally something where a non-database person is designing the database, probably a developer. The advantage you have with somebody like that doing the design is that it's probably going to be much easier to map between the objects that they're utilizing and the database itself, but it may not necessarily be the best database design. Figure 8.1 are alternative notations of various other types of databases designs that you might see along the way. Relationships of higher degrees, so you can have relationship types of degree 2 or higher than 2. 2 is binary, that's what we've seen so far. Relationship types of 3 degrees are called ternary, and so on. If you get up to n, it's n-ary. In general, an n-ary relationship is not equivalent to an n binary relationships. Constraints are harder to specify for higher degrees of relationships, and generally we avoid them. In general, 3 binary relationships can represent different information than a single ternary relationship. If needed, the binary and n-ary relationships can be included in the schema design. In some cases, a ternary relationship can be represented as a weak entity if the data modeling allows a weak entity type to have multiple identifying relationships. So here is an example of a ternary relationship type. The relationship is going to be between parts and supplier and project. So a given project uses a certain part made by a certain supplier, and all of those things together is how it's being done. Again, very, very rarely ever done. I don't know that I've seen this in the wild. Discussion of n-ary relationships. If a particular binary relationship can be derived from a higher degree relationship at all times, this is redundant. For example, the Taut-Deering binary relationship in figure 3.18 on the next slide can be derived from the ternary relationship offers. So here's the basic idea: Taut-Deering and offers, kind of redundant, and generally probably is uh, a general rule of thumb. If you have two things connected together that are very similar to the same thing, probably is redundant. Displaying constraints on higher degree relationships. The min-max constraints can be displayed on the edges. However, they do not fully describe the constraints. Displaying a 1, m, or n indicates additional constraints. M and N indicates no constraint. A 1 indicates that the entity can participate in at most one relationship that has a particular combination of the participating entities. In general, both min and max, or 1, m, and n, are needed to describe fully the constraints. Overall, the constraint specification is difficult and possibly ambiguous when we consider relationships of a higher degree, higher than 2. Another example of a university database to keep track of the enrollments in classes and students' grades. Another database is to be designed. It keeps the colleges, departments within each college, the courses offered by the departments, and the sections of those courses, and the instructors who teach those sections, and so on. These entity types and relationships among these entity types are shown in figure 320. And this basically is showing the university database kind of extended a bit further, showing attributes as well as entities. One of the nice things with software is that we can then kind of choose what we see. And sometimes you can also do something very similar at the physical level as well. Moving on to the chapter summary, ER model concepts are basically entities, attributes, and relationships. We talked about that. Constraints are important in the ER models. Using ER in a step-by-step mode. Conceptual schema design for the company, we went over that. ER diagrams and the notations associated with it, and alternative notations such as UML, others. And then the concepts of binary relationship types and those of higher degrees. We covered all that material. And as always, if you have any questions about the material that we've discussed, feel free to reach out to me. That's what I'm here for. Stay safe, and we'll talk again soon.